Okay, so one thing you could do with exponential functions is you can model things. We just learned that this is the general form, the general way that exponential functions look. Now, the a is always your starting value, your y-intercept, and then x, in this case, most of the time, is going to be representing time. Now, b, we said, was either growth or it was decay. Now, we're going to add one more thing to if it's growth or decay. If it's growth, you take 1 plus the rate of growth. Now, normally that rate is like a percent. So, example, if you are growing by 5%, you would do 1 plus 0.05. And so, what your b would be is 1.05. So, for decay, it's going to be 1 minus r. So, you might have something like halving. If something's halving, that is decreasing by 50%. And so you do 1 minus 0.5, and you would have a b of 0.5. Okay, so let's look at some examples here. For example, a city population. A city grows 5% a year. It also starts with a population of 32,000. What will the population be? And we'll do two examples here, like A, after 3 years. Okay, so we're going to do our general form, and instead of A, we're going to write the start amount, which was 32,000 people. Now for B, it's growing 5%. So 5% means we're going to add 0.05 to 1. And my B is going to be 1.05, and we'll put x up there. So after 3 years, to figure that out, we would do 32,000, 1.05, and we would put 3 up there. So I go to my trusty calculator, and I type in Alright, the power of 3, and I'm getting an answer of 37,004 people. So it's probably around 37,000 we can expect. Okay, so if we wanted to go further, B, we could say like 20 years. So the nice thing is, we get to use that model again. And we'll do 1.05, and we'll just put 20 in there. Okay, so you go back to your calculator. Instead of 3, you put 20. And I'm getting 84,905.5, and there are some other decimals behind it. The point here, though, is that you can't have half a person. So we would probably round our answer. And we'd also keep in mind that this is an estimate. So if we were to talk to people about this, we'd probably say around 84,900, around 85,000 people we expect after 20 years. One other thing that could happen, you could say 2 years ago. So it's the same thing. And then we do 1.05, but we do negative 2 in our exponent. Now if you're thinking, well, this is in the past and this city has been growing, so the population 2 years ago must be slightly smaller. And I'm getting, rounding, I'm getting 29,025. And that makes sense because 2 years ago we should have had a few less people. Alright, another example, like car values. A car is worth 23,000 brand new. It loses 20% of its value a year. This means it is going to be decay. How much will the car be worth? And let's say, how much will it be worth after 3 years? Okay, so set up our function again. We're going to write 23,000 as our start amount. Now our b is going to be 1 minus the percent, which would be 0.2. So we're going to put a 0.8 right there and put an x there. Now another way to think about this 0.8 is if I am decreasing by 20% a year, 80% is what would be left over at the end of the year. And so that's kind of how this works. Alright, so after 3 years, we'll do 0.8 and we'll put 3 up there. You go to your calculator. And I am getting a value of 11,776. Alright, it's lost about $12,000 worth of its value. And so we could have fun with this and we could say 10 years from now. We could do the same thing. We'll use the same model. 0.8 times to the 10th power. And we just have to change the 3 to the 10. And this car is now worth $2,469.6, and I'm rounding to the cent. But since we're estimating and we're predicting, it'd be probably worth around $2,500. Okay, and now one last one, and this is really important because in this situation we have to adjust our formula a bit. A bacteria population doubles every 3 hours. It starts with 40 cells. How many will be in the population after? Now let's just start with going with 6 hours. Okay, now to set this up, we know we're going to start with 40, but let's think about our B. If a population doubles, another way to say that is it grows 100%. So if you do 1 plus 1, you're going to get a B of 2. Now that makes sense because if you double, you're just going to multiply by 2 every time. Okay? So if it doubles every 2 hours, though, we have to make an adjustment to the time. So we're still going to put x, but we're going to have x over 3. So this is like x per every 3 hours. It means like after 3 hours, we're going to double. And so whenever you have like an every 3 hours, or per 5 days, or every 2 years, you always put the time as a fraction out of the per, or the out of part. And so to figure out this problem, we would do 40 times 2 to the 6 over 3 power. And so if you plug that all in your calculator, I'll go to mine right here, 40, 2 to the 6 over 3, which is really just 2, you're going to get 160 cells. And so if I asked like 15 hours, or better yet, let's do 17 hours, we would use the same model. We would do 2 to the 17 over 3. And after plugging that all into your calculator, I am getting about 2,031.8, so I'll round that to 2 cells. So we would say it would grow from 40 to about 2,000.